Our next speaker is Owen Milner, and he's going to talk about connected covers in Cubical Agda.
Okay, yep, thanks. This talk is sort of a summary of formalization work that I completed last year. I'm working on getting it into a state to be added to the Cubical Agda library. Until then, the code is available from the CMU GitHub organization page, and there's a link in the abstract for this talk. Okay. Connected covers were first studied by Catan and Sir and George Whitehead in 1952. The construction of the nth connected cover gives us a universal n-connected pointed space over a fixed pointed base space. If x is the base space, then we write x angle brackets n for the nth connected cover. Connectedness in general, and connected covers in particular, can be useful for calculating homotopy groups of pointed spaces. This is because of facts like the following. Here's a sort of trivial one. If x is n-connected, then pi n of x is 0. Less trivial is the Horevich theorem, which says that if x is n-1 connected, then the nth homotopy group of x is equal to the nth homology group of x. N has to be greater than 1. This was proven in homotopy type theory by Christensen and Skokala. Third useful fact is there's a fiber sequence where on the left we have an Eilenberg-MacLane space, and these are connected covers. It's maybe less obvious how to apply this fact than it is with the other ones, but both fact 2 and fact 3 are used in the proof of the finiteness theorem that's due to Tim Barton and Reed Campion. This work is sort of part of an ongoing effort to formalize this proof. In particular, the goal was to obtain formal proof in Agda of this last fact down here. Okay. So let x be a pointed space. We can define the nth connected cover of x recursively. The n-1th connected cover is just x, and then the n+1th connected cover is the fiber of the n+1 truncation map of x over the image of the point of the, the n+1th truncation map of the nth connected cover of x over the image of the point of the nth connected cover. Okay, the obvious point for -1 is just the point of x. The obvious point for the n+1th connected cover is the point of the nth connected cover together with the reflexivity proof that that's an element of the fiber here. Okay, here's the diagram. We have the n+1 truncation map over here on the right. We have the image of the point of xn. We're pulling it back to give the n+1th connected cover. Okay. All right. Alternatively, we could define the nth connected cover as the fiber over the nth truncation map of x, of the nth truncation map of x over the image of the point of x. There's a proof in the GitHub repository that these definitions are the same, but I thought about including it in the slides, but I don't think it's very illuminating to go from this definition to this definition. On the other hand, I mean, if we use this definition for the nth connected cover, then we can show that the nth connected cover satisfies a universal property. And then the sort of first characterization that I gave follows from that. This is a little bit more principled maybe than the approach I took in the formalization. Okay. So the nth connected cover is the terminal pointed n-connected space with a map into x. That's what I meant when I said that it has a universal property. What this means is that if y is pointed and n-connected, and f is a pointed map from y into x, then there's a unique filler here in this diagram. So here's f, here's the map from the nth connected cover into x. There's a unique filler up here This fact about connected covers appears in the paper by Christensen and Skokler on the Hurewicz theorem, which I mentioned before, and also in a paper by Buchholz and Riker on long exact sequences of homotopy n groups. Okay. It's pretty direct, now that we have this universal property, to observe that homotopy classes of maps from Sn plus k into x angle brackets n are going to be in bijection with homotopy classes of maps from Sn plus k into x, because the n sphere is always n minus 1 connected. So we have pi k of xn is equal to pi k of x if k is greater than n, and is equal to 0 otherwise, because, as I said, the nth connected cover is n connected. All right. Let's see. How much time? Yeah, 10 minutes at least, yeah. All right. Okay. Using either definition, we find a map from xn plus 1 into x of n. I've already mentioned that the goal of the work was to give a formal proof that the fiber of this map is this Eilenberg-MacLane space. There are a couple of extra tools that I haven't mentioned yet that go into the formal proof, so let's go through those. Here's Pupper's lemma. If x to y to z is a fiber sequence, then so is omega z to x to y. This map is the same as this map. Omega z is the loop space of z. The map here takes a loop to the pair consisting of the point of y and the loop, because the map from y to z is going to be pointed. The loop that's in here is already a proof that the point of y lies in the fiber of the point of x. Okay, sorry, of the point of z. Sorry. Anyway, Pupper's lemma follows from the pullback lemma. The pullback lemma says that if this square on the right is a pullback, then the square on the left is a pullback, if and only if the whole rectangle is a pullback. The whole rectangle is a pullback. This is one way to define the loop space. So because we're assuming that this is a fiber sequence, we're assuming that this square is a pullback square. This square is a pullback square too. All right. Okay. Second tool is Whitehead's principle, which says that if x and y are n-truncated spaces, and f from x to y is such that the set truncation of f is a bijection, and pi n of f of x from the nth homotopy group of x pointed at x, and to the nth homotopy group of y pointed at f of x is an isomorphism for each x and x, and each n greater than or equal to 1, then f is an equivalence of types. Whitehead's principle follows from the lemma that says that for every x and y, if the set truncation of f is a bijection, and the map between the loop spaces given by f is an equivalence of types, then f is an equivalence of types, and here's, we're sort of getting towards the end of the talk, so I decided to include a little bit more Agda code from here on. So here we have the two types, here we have f, a map between them, here we have the hypothesis that the set truncation is a bijection, here we have the hypothesis that the map between the loop spaces is a bijection, sorry, is an equivalence, the conclusion is that f is an equivalence. And here's the formal proof of Whitehead's lemma. You can see we're going by induction, and in the induction step, we're appealing to the previous lemma. Okay. All right. One important corollary of Whitehead's lemma is that if x is n-connected and n plus 1 truncated, then it's equal to this Eilenberg-MacLane space. Something a bit stronger is true, actually. This sort of k-blank n plus 1 construction is part of an equivalence between the type of abelian groups and the type of n-connected n plus 1 truncated types. Okay, proof of this appears in Floris van Doorn's PhD thesis. We're not going to use this stronger statement, we only need the weaker statement, but I'm just pointing it out. Okay, we're ready to get back to the goal. All right, it follows from the corollary and some of the facts about connected covers that we mentioned earlier, in particular the calculation of their homotopy groups and the fact that the nth connected cover is n-connected, that the n+1 truncation of the nth connected cover is equal to this Eilenberg-MacLane space that's here. All right. So using the first definition of the n+1th connected cover that I gave at the beginning of the talk, we have this. This is a fiber sequence here, right? So using Pupa's lemma, we have a fiber sequence like this because the loop space of k n+1 is k n, right? So here's the Agda code for this last sort of part of the project. If we have, so here's the fiber sequence consisting of the all the sort of indexing is off because Agda starts counting in the wrong place. But here's the n+1 connected cover, the nth connected cover, the Eilenberg-MacLane space. That's the first fiber sequence I showed you. Here's the observation that because the loop space of the n+1th Eilenberg-MacLane space is just the nth Eilenberg-MacLane space, it's sufficient to find a fiber sequence like this with the loop, and then the n+1th connected cover, and then the nth connected cover. And then here we're applying Pupa's lemma to give us this fiber sequence that we need using that fiber sequence. Okay. All right. So there's some references. I still have, I guess, 10 minutes, I think, something like that. Yeah. All right. So in the abstract that I submitted, I mentioned the example of S1 wedge S2. It's a fact that the first connected cover of this space is the wedge of Z many copies of S2. It's worth saying sometimes the first connected cover of a space is also called the universal cover, at least the first connected cover of a path-connected space. Right. Given this, we can calculate pi2 of S1 wedge S2 because by a previous fact, it's just going to be pi2 of the wedge of copies of S2, which is, by the Hurewicz theorem, is going to be the homology group, right? The second homology group of this space. And then this is this direct sum. Okay. I'm going to be way under time. But why should we think that this is the first connected cover of that space? I don't have a complete proof, but the connected cover by definition is this sigma type, right? This is the fiber, the truncation map over the point. But the truncation of S1 wedge S2 is equivalent to S1. The truncation map then becomes the pointed projection from the wedge into S1 under this equivalence. So we can rewrite the connected cover as this sigma type, right, where this is the pointed projection. And now there's a map from the coproduct of Z many copies of S2 into this sigma type, where we take the point, so X is a point in S2, we take the point X in the Z component of the coproduct into the the right inclusion of that point in S2 together with the loop sort of Z many times, because remember that this projection takes every point in S2 to the point of S1 and loops on S1 are the same thing as Z. So finally, I think any map from here into another type, which sends all the base points to the same point, should factor uniquely through this map, and that would be a proof that this type satisfies the universal property of this type, and so that they're equivalent. Okay, that's everything that I had to say.
Are there questions? Thorsten, yeah.
Yes, I just wonder, what aspects of Cubical Agda did you use, and what was the main sort of technical difficulties? Did you have to fill some cubes or fill some? Were there some interesting arguments?
There was not very much interesting cubical work here. I think the utility of Cubical Agda in this case was stuff about kind of how the elimination rules for higher inductive types work in Cubical Agda that I think I would only have noticed if I had at the same time tried to do the same proofs in vanilla Agda. As a matter of fact, there's very little that's cubical in this work.
Thank you.
Okay. Other questions? At the back. Yeah.
So how far away from the full self-finiteness theorem are you formalization-wise now that this has been done?
Now that this has been done, the only other thing that stands out to me is formalizing facts about what are called stably almost finite spaces, which are defined in the paper. So that's going to take some time, but once that's finished and once the Hurevich theorem for cellular homology is done, I think that'll be everything. I'll have to check again, but I think that'll be everything.
Okay. Other questions? No? Then let's thank our speaker again.